For this problem, we're going to have not just disjunctions, but disjunctions inside disjunctions, or nested disjunctions, on both the given side and the goal side. So there's going to be a lot to keep track of. In particular, we're going to have not just a case 1 and case 2, but a case 1a and a case 1b. So here's the problem. Suppose A, B, and C are sets. Prove that A union B symmetric difference C is a subset of A symmetric difference C union B symmetric difference C. So let's try and draw a picture of this and also remind ourselves what a symmetric difference is. I'm going to try and draw a Venn diagram here with 3 sets in it. A, B, and C. And set on the left side here is A union B, which is these 2 circles. Symmetric difference C, and you can think of this as the union of the 2 sets minus the intersection. Okay, so the union of A union B and C would just be everything, and the intersection is these 3 little pieces in here. And so I'll try and color in everything else. The union minus the intersection, something like that, together with this piece down here. That's the left-hand side. And then the right-hand side, we think about A symmetric difference C. That's going to be the union of A and C minus their intersection, which would be these 2 pieces up here, and this piece, and as well as this piece here. And then B symmetric difference C would be the union of B and C minus their intersection. So that would be these 2 pieces up here, together with this one and this new one as well. Okay. If you followed that, then you see that indeed the left-hand side is a subset of the right-hand side, but the right-hand side is larger in general, right? If there are sort of some elements that belong in either of these 2 spots in the Venn diagram. Okay, so we'll want to keep that in mind for part B. All right, so let's try and work this out. Here's the statement we're trying to prove. And definition of a subset gives us this. If we let x be arbitrary, we can eliminate that universal quantifier. And to prove the conditional statement, we'll do direct proof. Move the antecedent over as a given. And now we got to use some definitions. So the symmetric difference. Now, when I was making the picture, I said it's the union minus the intersection. But another way to define it is that it's basically all the elements that are in one of the sets but not in the other. Okay, and so in this case, that would mean that x is the first set minus the second set, union the second set minus the first set. Okay. And we can do the same thing over here for both of the symmetric differences. For example, we get that A symmetric difference C is A minus C union C minus A. And we can take this union here, that x is in the union, and break that up into a disjunction. X is in the first set or x is in the second set. And we can do the same thing over on the goals side. And now that we have a disjunction on the given side, we can break that into a couple cases. Case 1 and case 2. And I'll just bring down our goal into each case, same goal. Okay, and now we have some more definitions to work out. This is a set difference, right? So, and it's also a union, so the union becomes x and a union, x and a or x and b, and then set difference gives us and x is not in C. Whereas in case 2, we have that x is in C and x is not in A union B. We'll work that out a little bit further later on. And then on our goals side, we can take these other unions as well and write those as disjunctions and drop some parentheses because they're not going to make a difference. Right, so for each goal, we just have a disjunction of sort of 4 different possible statements. Now in case 1, we have a conjunction, and we can just take that as 2 separate givens. Same thing in case 2. And Well, now we should think about exactly what we're going to prove in case 1. It looks like we're going to know that either x is in A or x is in B. And so we're probably going to end up proving either the first statement here or the third one. Okay. So I'll put those as our goals. And in case 2, we're going to know that x is in C. And so we're probably going to be proving the second or the fourth statements from up here. So I'll bring those down as our new goals for case 2. Now in case 1, we do have another disjunction. And so that gives us our case 1a and case 1b. And then the other given, x not in C, will come down into each of those cases. And looks like in case 1a, we're going to be able to prove that x is in A minus C. And in case 1b, we'll be able to prove x is in B minus C. Okay. In fact, let's just say that we're done with those cases now. And we can move on to case 2. Which starts out that way. And then we have x not in A union B. And I want to figure out what that means exactly. That's the negation of the statement x in A union B, or x in A or x in B. And to negate that disjunction, we want to turn it into a conjunction, flip over our symbol there in the middle, and also to negate each of the statements. Okay, so for x to not be in A union B means that x is in neither A nor B. Makes sense. And, well, let's see. We need to prove that x is in C minus A or that x is in C minus B. And in fact, it looks like we could prove both of those, right? But we just need one. So let's just drop that x not in B and keep the x not in A. And we'll keep the goal of x in C minus A. And we've got it. Okay. So that's how things work out. Now let's see if we can write all that down. First thing we did was to let x be arbitrary to get this conditional statement as a goal. And then we tried direct proof by supposing that we knew the antecedent, okay, which left us with this goal. So we want to write let x be an arbitrary element of A union B, symmetric difference C. And we're going to show that x is in A, symmetric difference C, union B, symmetric difference C. Okay, and then next we could help our reader to decode this assumption here by using definition of symmetric difference and then turning our union into a disjunction to arrive at this given. Okay, so let's just say we know that x is in A union B, not symmetric difference, just minus C, or x is in C minus A union B. Good, okay. And with that disjunction, we got a couple of cases. So from this we got case 1. And we wrote out what that meant, which got us down here. And we broke that up a little bit to get here. And then we had another disjunction, so these came down as case 1a and gave us our goal. And these came down as case 1b, which gave us a different goal. And that took care of case 1. So let's see if we can put that down. Case 1, suppose x is in A union B minus C. Okay, so then we had then either x is in A or X is in B, right? And then my parentheses are going to turn into a comma here. And X is not in C. Good. And I want to say that, so there's a couple cases there in OR. And in the first case, which is really my case 1A, although I'm not going to label it that way in my proof because that's a little confusing. In the first case, X is in A and it's not in C, so it's in A minus C. And in the second case, X is in B minus C. And there we go. And we'll come back after we do the other case as well and say how this connects to our goal up here. Okay. There are a number of simplifications we did here on the goal side, which we haven't mentioned in our proof yet. All right, well, anyway, I'm going to come to case 2, which originally came from up here, and then there, and then we wrote it out, and we split it up, and we figured out what X not being an A union B meant, and we put the negation inside, and we eventually got all the way to here, which gave us the goal we needed. So we could summarize that process by saying, suppose X is in C minus A union B. Then the definition of that is that X is in C and X is not in A union B. And from that, it follows that X is not in A and X is not in B. As always, I'm taking this conjunction and changing it into some English so it's a little easier to read. And then we can say, therefore, X is in C minus A. That was our conclusion. And I'm going to put in here and X is in C minus B. Okay, we don't need that for the proof, but I'm indicating that we could derive that from the X not in B here together with the X in C, and I'm putting in parentheses to help the reader understand that yes, that does follow, but we don't need it. Okay, and all right, so we should make sure that our reader understands that these results, X is an A minus C or B minus C or C minus A, do connect up somehow to our what we said we were going to show up here. And the way that happened over in our table here was, well, that came from that, and these were a couple of the possibilities in this huge disjunction here, and at some point that was written in terms of a union, right, all the way up here, which was a definition for this set involving symmetric differences, which we said we were actually going to prove X belongs to. And same deal with X in C minus A. Okay, so that was that one right there. We also could have done this one, and all of these eventually fed back up to here. So to summarize that, I think I can just say in either case, meaning in case 1 or case 2, that's how I'm going to write it. X is in this set that we said it was, because that set is equal to the union of these 4 sets. Okay, and in case 1 and case 2, and case 1A and case 1B, we've always shown that X is in at least one of these sets. So at long last, that takes care of part A. And now for part B, which is going to be quite a bit quicker, I have got the answer down there for us already, or one answer I should say. Find an example of sets A, B, and C such that these two sets are not equal. Remember, we know that the left set is always a subset of the right set, but in general the right set might be larger. And if you remember, in our Venn diagram, let me draw it again real quick here. We had A, B, and C. It was when there are elements in sort of these spots that, well, those elements would be in the right side but not in the left side. Okay, so we just need to come up with an A, B, and C such that that's the case. And we actually only need an element in at least one of those. So one boring thing to do would be to just let A and C both be the set containing a single element, say the number 1, and to let B be the empty set. And that would definitely give us an inequality here. But just to be a little more interesting and also maybe a little bit easier to digest, I've decided to imagine that C is a set consisting of elements 1 and 2, and then A is the first half of that and B is the second half of that. And then A union B would be the entire set C, right? And so this is just C symmetric difference C, and there's no difference between those. So the symmetric difference is the empty set. Whereas if we take A symmetric difference C first, then we're going to get 2. And B symmetric difference C is 1. And then if we take the union afterwards, we get 2 union 1, and we get the entire set 1, 2, which just happened to be C. And so the point is, in this case, the right side of the equation is definitely strictly larger than the left side. So that example will do, and you can come up with lots of other ones as well. Okay, that does it.